Having discussed temperature and the ideal gas law, we're ready to tackle kinetic theory. Kinetic theory is at the crux of thermodynamics, so it's one of the most important parts of everything we need to talk about. Now, this can get quite complicated because since you're dealing with billions of molecules would be an understatement. As you saw, Avogadro's number is 10 to the 23rd, so 1 mole of a substance is 10 to the 23rd molecules. It's a little difficult to calculate the speed and motion of 10 to the 23rd molecules all at once. So we use a lot of statistics. And in the statistics, we need to make a number of assumptions. First of all, we have a large number of molecules, all of them moving randomly. And so if you take an average, they roughly have the same. Uh, you can take an average of them all. But individually, they all have random directions and random speeds. Another assumption is that these molecules are far apart from each other. Now, by far apart, we're not talking about like 10 or 12 centimeters. We're talking about take the diameter of a molecule. The closest molecule would probably be a couple diameters away from that molecule. So we're dealing with far apart on the molecular level. We also assume that all molecules are going to obey the laws of classical physics or classical mechanics and interact only when colliding. In other words, each individual molecule follows all the same laws that we learned in first semester physics on motion, forces, work, energy, so on. We also assume that all collisions of molecules are perfectly elastic. Okay, so here's the kinetic theory. Top left box, you have a lot of molecules moving in all sorts of directions. We're going to look at just one molecule. So here in the bottom figure, you have one molecule. It impacts a wall and bounces back. Okay, so we can measure the force of that impact as the change in momentum divided by the change in time. Momentum is just calculated as mass times velocity. Well, what's the change? Well, at first we were going a velocity negative Vx, but then after the collision we were going positive Vx. And so Vx minus a negative Vx gives you 2Vx. So our change in momentum would be 2 times mass times Vx. How much time does this take? Well, this comes from the definition of velocity. Velocity is change in position over change in time. So change in time would be your change in position over your velocity. Well, how far do you go? Let me clear this box up a little bit here. Well, you travel some distance L, then you bounce that same distance L back. And so you travel a distance of 2L. So it becomes 2L over V. If you simplify all that, then you get that you have a force of mass times Vx squared divided by L. Now this L is going to be arbitrary, it's going to disappear in just a minute, so don't worry about what L really is. Okay, so that is the force of one molecule on the edge of a container in an ideal gas. Now, if we want to know the force of all the molecules colliding with the wall, then we need to multiply by the number of molecules we have. So it's exactly the same equation, we're just multiplying by n. Now, this is all just the forces in the x direction. If we want the total force, then we have to add the force in the x direction plus the y direction plus now the z direction, because remember, we can't work in 2 dimensions anymore. A gas is a 3-dimensional substance. And when we add forces, when we add 3-dimensional vectors, well, let's start off simply with a 2-dimensional vector. Pythagorean theorem. A squared plus b squared equals c squared. Or I should say F, because we're dealing with forces. So force squared equals a squared plus b squared. But if you deal with 3 dimensions, guess what you do? You just add that 3rd dimension squared. Makes it pretty easy. Now, so that means that f squared is equal to fx squared plus fy squared plus fz squared. Now, I'm going to make this short and easy for you and just say that the only other vector involved in this equation is the velocity. And so that means that your total velocity squared, oh, you know what? I need to come back and describe one more thing before I do this. Notice how there's a line over Vx squared now. That's because now we need to take the average of all the square velocities. Up here, the force is proportional to the velocity squared. And so the total force is going to be the average of all those velocities. And so the average Vx squareds would equal Vx of molecule 1 squared plus Vx of molecule 2 squared plus plus Vx of molecule n squared. Excuse me, I'm going to use capital N here. But anytime you do an average, you add up the values and then you divide it by the number of values you have. And that's where the average Vx squareds come in. Okay, now let's get back to this, that the magnitude squared is going to be the sum of the squares of the components. It's going to be the same for the velocities. However, I want you to note that since there are 10 to the 23rd molecules in 1 mole of the gas, and they're all moving totally randomly, then there's not really much of a difference between x, y, and z. They're going to have roughly the same average values. Therefore, your average v squared is going to be 3 times vx squareds, or vx squared is going to equal 1/3 of your v squareds. And if you plug that in, this is the equation you get. Force is equal to mass over length times n times v squared over 3. Okay, that's force. We're moving on to pressure now. And the reason why we're doing pressure will come clear in the next slide. We're working towards the ideal gas law, which is in terms of pressure and volume. So pressure is force divided by area. So you take this equation and you do the exact same thing, you just divide by area. Well, when you divide by area, you've got area times length. That gives you a volume. And so it just replaces it with that. Now, if we multiply on both sides by volume, we get pressure times volume equals 1/3 n mv squared. 2 things I want you to note. PV should look familiar. Ideal gas law, so let's replace that with NKT. We want to deal with this version of the ideal gas law since we're dealing with capital N over here. The other thing I want you to notice is this mv squared. Where have we seen mv squared before? Kinetic energy, but that's 1/2 mv squared. So if we multiply this by 1/2, we have to, whenever we multiply by a number, we have to also multiply by its reciprocal. So we have to multiply the whole thing by 2. So this becomes 2/3 n times 1/2 mv squared. The n's cancel out. And if you solve for the 1/2 mv squared, you get that the average kinetic energy of molecules in an ideal gas equals 1/2 of the mass times velocity squared. Now we're talking average velocity squared, or mean velocity squared. And that's going to equal 3/2 kT. Bottom line, the average translational kinetic energy is proportional to temperature. Now, at the beginning of this chapter, we defined temperature as a measure of the average kinetic energy of molecules And now you can see exactly why we defined it that way. Temperature is a measure of the kinetic energy of the molecules in an ideal gas. Now, when you solve problems using the kinetic theory, you may be given the kinetic energy and need the velocity. You might be given the kinetic energy and need the temperature, or you might be given the temperature and need the velocity. Any one of these three sides of the parts of the equation they're all equal to each other, so you can use any part of it that you need to for the question that you're given. Now, what if we wanted to find the average velocity of the molecules, not just the average kinetic energy, but the average velocity of the molecules? You can't do it traditionally, because since there are 10 to the 23rd molecules in 1 mole of an ideal gas, and they're all truly random, then every time you have a molecule moving to the right at 2 meters per second, you're going to have one moving to the left at 2 meters per second. And every time you have a molecule moving one direction, there's bound to be one moving in the opposite direction at the same velocity. And so the average is going to equal 0. They're going to cancel out. But we can use the kinetic theory equation. Remember that average kinetic energy is equal to 1/2 mass times average velocity squared. Well, solve for your average velocity squared. That's going to be 2 times your average kinetic energy divided by your mass. But this is the average of your velocity squareds. This is a problem and yet a huge help at the same time. Since we're averaging the v squareds, all the negative values go away. So all of a sudden, direction doesn't matter. It works. We can now find an average. So we find the average, but here's the problem. Our average v squareds have units of meters squared per second squared. We need to get rid of those squares now. So what you do is you take a square root on both sides, and you get yourself an average velocity. So we call this our RMS velocity, meaning root mean square. RMS means root mean square. It's a typical statistical way of looking at average values when average values are likely going to be 0. And we will deal with more RMS values when we start dealing with electricity. Anyway, so there you go. RMS velocity is going to be the square root of your average v squareds. Now, kinetic energy, we also know from kinetic theory, that's going to be 3/2 kT. So if you plug that in, then you get this form of the equation right here. So the RMS velocity is going to be the square root of 3 kT divided by m. All right, one last thought on the kinetic theory, and that is the distribution of molecular speeds. Remember, this is a statistical analysis. So if you were able to measure the speed, not velocity, but speed of all the molecules in an ideal gas, you would get a distribution that looks something like this. You'd have a handful of molecules with a small velocity down here, handful of molecules with a very large velocity, but for the most part, most of your molecules have a velocity in this range. In fact, here, the peak value of our curve is Vp. That's the most probable speed of velocities. Not an average, it's a most probable speed. However, we can't get that by using an average, like we saw in the last slide here. If you try and find an average velocity, you're going to get 0. And so you can't really find a statistical mean, the same way we traditionally do. So we use the RMS velocity, which is going to give us a slightly different value, but so even though it's a little bit off, it's close enough. It gives us a very good indication of the average speed of molecules. Now, remember, that the kinetic energy is going to equal 3/2 kT. So if your temperature increases, then so does your kinetic energy. If your kinetic energy increases, so does your velocity. So we would expect all of this information, all of this graph, to move to the right if T is increasing. So at higher temperatures, we expect everything to shift to the right. On the bottom left, we're looking at two graphs. One is the average velocity of, is the speed of, the distribution of the speed of an ideal gas, molecules within an ideal gas. One at 0 degrees Celsius, one at 37 degrees Celsius. And what we see is here's the most probable speed, Vp, at 0 degrees Celsius. And here it is at 37 degrees Celsius. Sure enough, the average velocity increases as temperature increases. And so it's safe to say that temperature is a good measure of the kinetic energy or the velocity of molecules in an ideal gas.